How you doing?
Good, how are you?
All right.
Looks like it might just be me.
Yeah, I don't know. I get more in-person students at the 8:30 class.
Yeah,
You'd think it would be the opposite, but
right. People wanting to stay in their bed.
yeah.
And is it actually pronounced aqueous? Because at my school we always pronounced it aqueous.
Did you have a British teacher?
Mm-hmm.
No.
We were learning technically British curriculum because I was doing IB.
Okay.
So that might be why.
Yeah, the only people I've heard use the aqueous are people who have a British background.
Yeah, because this is the first time I've heard it pronounced aqueous.
Oh, really?
Yeah.
My advisor in grad school was British, and so he had some different ways of pronouncing different things.
Mm-hmm.
So
Yeah, for 3 years I learned it was aqueous. So.
yeah, today you'll hear me say aqueous.
Mm-hmm. And my lab teacher, Susan Scott, she pronounces it aqueous too. So I was like, that must be right there.
Yeah, I don't know if there's a right or wrong. I think it's like I said, when I've heard people do that, it's been more people who have some type of British, UK type background. I think it is just us.
Mm-hmm.
So can the people on Zoom see the slides and hear me okay?
Yep.
Thank you. Okay, so we'll go ahead and get started. Today we're gonna talk about Chapter 4, reactions and aqueous solutions. Before we get started on that, I do want to remind everyone that Wednesday we're going to have our second quiz, and that'll be on Chapter 3. So we're covering Chapter 4 today, and we'll finish it up on Wednesday. And then after we finish the Chapter 4 stuff on Wednesday, then you'll have a chance to take your quiz. You can come into the class and take the quiz, or you can take it remotely. It's up to you. Once again, it'll be timed like last time, and you'll access it through Canvas. So, all right, let's get started on chapter 4 then. So when we talk about solutions, what we're talking about is a homogeneous mixture. And the mixture can be of 2 or more substances. The substance that's there in the greatest amount is called the solvent. And the other substances that are present, which are lesser amounts, are known as solutes. And so when we're talking about solutions where the solvent is water, we call those aqueous solutions. When we think about how substances dissolve in water, there's a couple different ways that that happens. And it depends on what type of compound it is. If it's an ionic compound, then the dissolution happens through dissociation. And in that case, the water surrounds the separate ions. So you think about ionic compounds, you typically have a cation and an anion, and because it's ionic, it dissociates into the cation and anion, and then the water solvates around that. So what you're left is with the cations and anions separated and kind of floating around in the water. Molecular compounds interact with water, but they don't dissociate. And so in that case, you're not getting ions formed, you're just getting the molecules with water molecules around them. There are some molecules that actually react with water when they dissolve, and so that's a third way. In any of these cases, though, you have this solvation. In other words, you have the water molecules for the aqueous solution surrounding either the ions or the molecules, or if there's like a reaction, the reactant products. And so the 2 examples here at the bottom of the page, one is sodium chloride. So sodium chloride is an ionic compound. So you get dissociation of the sodium ions, the sodium cations, and the chloride anions. And then you get the water molecules kind of surrounding each of those ions, and all that's floating around in the solution. The other example here is methanol. So methanol doesn't ionize, it stays as methanol, but you get the water kind of surrounding the methanol molecules. And so that's that second interaction that we talked about where they don't dissociate. One term that you often hear is the term electrolyte. So let's talk about what that means a little bit. And if you think about electrolytes, where at least I hear it a lot, is with the sports drinks, Gatorade, Powerade, things like that. They'll say you need to replace your electrolytes. Electrolytes are important for good body function and things like that. So let's talk a little bit about what that means. If something is a strong electrolyte, then we say it completely dissociates when you put it in water. So the sodium chloride on the previous slide, that would be an example of a strong electrolyte, because we put a sodium chloride molecule in water, the sodium and chloride dissociate from each other, and you get a bunch of sodium ions, sodium cations, and a bunch of chloride anions floating around in there. Compounds that are strong electrolytes allow you to conduct electricity. So that's how electricity is conducted through an aqueous solution, is through those ions. If you have a weak electrolyte, then that means it partially dissociates. And so we'll have some examples of that in a little bit. But when we say something partially dissociates, if we think back to how we've been writing our chemical equations, we've had the arrow just going one way. So that's an example of something that totally dissociates, where it starts out one way, then goes all the way to the products. And so there's no back and forth, no equilibrium is the term that we use. If something partially dissociates, it means that not all of it goes into those ionic forms. Some of it stays in the molecular form. If that happens, then we say that's a weak electrolyte, because you don't have as many charged ions in the solution to be able to help the electrical charge be moved around in the solution. And then finally, a non-electrolyte is something that doesn't dissociate at all. And so in the examples at the top, we see pure water. Pure water itself doesn't conduct electricity. Now, one thing I'll say about that is it's really, really difficult to make pure water. It's very difficult to remove all the ions out of water. And so if you're able to do it, then you'll find it doesn't conduct electricity because you've removed all those ions. But practically speaking, it's pretty hard to do. The second one is a sucrose solution, so sugar. And I think we all know sugar dissolves pretty easily in water. So dissolving it's not a problem, but the sugar molecule itself doesn't ionize when it goes into water. So there's no dissociation at all with the sugar. And because of that, it doesn't conduct electricity. And then finally, the sodium chloride, which we mentioned before, that goes into solution. The sodium and the chloride ions dissociate. You have a bunch of positively charged sodium ions, a bunch of negatively charged chloride ions. That conducts electricity real well. So if we then link that back to the sports drinks in that, what they're talking about is having electrolytes, is they're talking about having these compounds that will dissociate. Because if you think about the example here, they're saying that we can light this light bulb up. In other words, we can get electrons to flow by having a strong electrolyte in there. There's a lot of processes that go on your body that have a similar electrical type of thing. And so you need those electrolytes in there for it to be able to function properly. So that's kind of the linkage to the sports drinks with the electrolytes that you hear about in the commercials and stuff. And we see that if you drink just pure water, like I said, it's hard to get pure water, but if you drink pure water, you don't get those electrolytes, and it doesn't help with those electrical type transport things you might have an interest in. Okay, now we're gonna talk a little bit about that term equilibrium that I mentioned. So the first equation, HCl, hydrochloric acid, dissociating into hydrogen ions and chloride ions, that's a strong electrolyte. And we see that when we write that chemical equation, we have HCl going to H plus Cl minus. We have the arrow just going in one direction. That tells us if you put HCl in water, it's going to dissociate fully into those two ions, the hydrogen and chloride ions. And something like that dissociates into those ions, that's a strong electrolyte. Well, below we have acetic acid. That's the CH3COOH. That's acetic acid. When we put acetic acid in water, that's soluble, but what we see is that it doesn't totally dissociate. So in this case, we see that acetic acid goes to hydrogen ions and acetate ions. So that's acetate is the CH3COO minus. But let's look at the arrows there in this chemical reaction. We have one going to the right, but we also have one going to the left. That's telling me that there's some type of equilibrium happening. So if I were to take that solution and then analyze what was in it, it would be the acetic acid molecule, so the molecule on the left, plus the hydrogen ion, plus the acetate ion. I'd find concentrations of all three of those in the solution. And so the equilibrium is just the proportions of each of those that is kind of the steady state or the normal state of that molecule when you put it into water. By contrast, if I took HCl and put that in water and then analyze what was in there, I wouldn't find any of the HCl molecule. I would only find the hydrogen ion and the chloride ion. So that's kind of the difference between strong electrolyte and weak electrolyte. And like I said, one of the key things is when we write those chemical equations, the strong ones are just going to have an arrow going one way. The weak one's going to have the arrows, one going to the right and one going to the left. The other comment about the acetic acid is we're all pretty familiar with acetic acid because that's what's in vinegar, is acetic acid. So if you ever use vinegar for cooking or anything, that's a dilute acetic acid solution. So we know that ionic compounds that dissolve in water give us a cation and anion. But not all ionic compounds are soluble in water. They don't all dissolve in water. And so a lot of them do, most of them do, but there are some that do not. And so in this table, we have some guidelines for solubility of ionic compounds in water. And then on the next page, we'll have some more. This is one of those tables that you're going to have to just memorize. You're going to have to learn some of these solubility rules. So this isn't meant to be every compound, but these are ones that are a little more common and the ones that I'll be concerned about in the tests and quizzes and stuff. So what we see here are some anions. And so compounds that contain these anions are typically soluble. So they're ionic compounds and they are typically soluble in water. So that means they'll dissolve in water. So nitrate, acetate, chloride, bromide, iodide, sulfate, all of those typically are soluble if the compound has that. As with most things, of course, there are some exceptions. So for nitrate and acetate, there's no real key exceptions to those. But for the halogens and then sulfate, there are some exceptions. So we see that for the halogens, chlorine, bromine, iodide, we see silver, mercury, and lead. Those, if those are the cation associated with it, then you'll get a precipitation. So it's not soluble. So silver chloride in particular is a real common one that you see. There's a titration that people do to determine the amount of chloride in a sample, and that centers around that silver chloride precipitation reaction occurring. So if when you're learning these solubility rules, you get the general trends from these anions, but then there are a few exceptions to when things are soluble or not. So remember that if you have silver, mercury, or lead associated with chloride, bromide, iodide, that those are not soluble. And yes?
I was wondering if fluorine followed the same rule as the other halogens.
You know, I don't know. I don't know the answer to that. I don't think, it wouldn't surprise me if it did, but you just don't work with fluoride compounds as much. For like, you know, silver, AgF and that, I don't think I've ever recalled seeing that anywhere. So I don't know the answer to that. And then finally, the sulfate, the SO4, we see there are a few exceptions to that solubility also. Some anions that are typically insoluble, we have sulfide, carbonate, phosphate, hydroxide. But of course, there are exceptions to this. The general exception is if you have ammonia as the cation associated with it, it's usually soluble. So ammonium salts are typically soluble. The other thing you'll see the alkali metals. And if we remember, the alkali metals were that first column on the left. So that was things like lithium, potassium, sodium, stuff like that. So if that is the cation, then even these anions will be soluble, even though they're normally not. One easy way, at least for me, to remember those 1A alkali metal cations is you think of like sodium and potassium, which are in there, and you think of table salt, sodium chloride, things like that. So things that you would use in your normal day life. And so those are soluble. And so alkali metals, those 1A, group 1A stuff, and then ammonia. So the ammonium ion, NH4+, those will be exceptions, and then those resultant compounds with these anions will be soluble. So this table, where we have some information on soluble ionic compounds with some exceptions, and then some insoluble ionic compounds with some exceptions. This is a table that I would expect you to know. And one reason you'll need to know that is you'll need to use some of this information, we'll see in a little bit, in predicting reactions of what's going to happen when you react certain chemicals together. Do you get something precipitating out, or does it all stay in solution, or what exactly happens? So if you don't remember the rules on this or the guidelines on this, it's a little difficult to make some of those prediction reactions. Okay, let's talk a little bit more about electrolytes and non-electrolytes. So if you have soluble ionic compounds or soluble molecular compounds, if it's a soluble ionic compound, it's always going to be a strong electrolyte, because by definition, those ionic compounds want to dissociate fully. If you have a molecular compound, then it depends on what kind of acid or base it is. If it's a strong acid or strong base, then you'll get full dissociation, and then it'll be a strong electrolyte. So the hydrochloric acid is an example of that. For a strong acid, that dissociates fully, as we saw earlier, and so that would be a strong electrolyte. Sodium hydroxide is a strong base, and so that's an example of, you put that into solution, it dissociates fully. Once again, because it dissociates fully, you get a strong electrolyte there. When we look at weak acids and weak bases, and a weak acid or weak base is basically any of them that isn't a strong one. And so when we get to that, something like the acetic acid, for instance, that we saw, there we have some type of equilibrium, and it's not going to be fully dissociated, so we call that a weak acid. Ammonia is probably the easiest definition for a weak base, because that doesn't dissociate fully either. If you have compounds that aren't acids or bases, then you typically don't have any type of ionization or dissociation going on. And in that case, you're going to get it'll be a non-electrolyte. So once again, that sugar example that we had earlier, it goes into solution, it's soluble, but because there's no ions being formed, you got to have ions to be able to have, call it electrolyte. Because there's no ions being formed, it's a non-electrolyte. So try and remember that distinction between an electrolyte and a non-electrolyte, and then also the distinction between a strong electrolyte and a weak electrolyte. Let's talk a bit about precipitation reactions. So if you have two solutions, and each of them contains an ionic compound that's soluble. So in other words, you have two beakers. In each case, the material you put in there dissolved in the water and fully dissociated. But sometimes when you then combine those two beakers, even though individually they are both soluble and dissociated when they're by themselves, when they're mixed, now you get combinations of cations and anions that start giving you, if we go back to that table about solubility, you start getting combinations that indicate that we're going to get a precipitation occurring. And so this is what we call precipitation reactions. And the solid is called a precipitate. So in this example here, we have potassium iodide, Ki. And so if we put that into solution, everything's fine. The potassium and iodide dissociate, so we have K+ ions, we have I- ions, and those would be floating around. If in another beaker we have the lead nitrate material dissolved in water, we have lead ions floating around, positively charged lead ions and negatively charged nitrate ions, then we would be fine there. If we then took those two beakers and combined those solutions together, well, now we've got potassium ions, iodide ions, lead ions, and nitrate ions. And we know the nitrate ions, no matter what we match up with from our solubility rules, we know that that will stay in solution, but we know that one of the exceptions for the iodide was lead. So normally the iodide is in solution when it's in water, but if it's matched up with lead, that was one of our exceptions from the table. And so now we see the lead iodide forms this yellow precipitant at the bottom. So the other thing I want to point out is last chapter, we learned a bit about putting information about the physical state of the compounds in the parentheses right after the compound. And we see that here. We see in this reaction at the bottom of the page, we see a little AQ after the Ki and after the lead nitrate and after the potassium nitrate. We see after the lead iodide, we have a little S. So that tells us that that's a solid material. So that's one of the helpful things about having those little designations like that. It helps us identify which of the compounds is still in solution, still in these case ionized, or has reacted and precipitated out. So how do we know if a precipitation reaction is going to occur? So if a precipitate forms when strong electrolytes are mixed, we have to, in order to figure that out, we have to go back to our solubility guidelines that we talked about earlier. So what we would do is we would look at the ions that are present in the reactants. So we would look to see which things dissociated. We're saying they're all strong electrolytes, so they all should be dissociated. And then we look at those cation anion combinations that we could have, and are there any there that would result in, based on our guidelines, based on a combination that is insoluble. So we would get something that precipitates out. So here in this case, we have magnesium nitrate, we have sodium hydroxide, and we have that going to magnesium hydroxide and sodium nitrate. And what we see is that in this reaction, if we go back to our rules, we know that the magnesium hydroxide will form a solid. And so we'll have a precipitate of that. So this is what I was saying before is going back and looking at that table of those guidelines on solubility of these ionic compounds is important because it helps us do things like this, predict whether when we combine solutions, we're going to get anything precipitating out or not. So there's a term called metathesis. And this comes from a Greek word known as to transpose. And so metathesis is just a fancy word for saying exchange. And so these reactions like this, like the one we just talked about forming the magnesium hydroxide, where you have these ionic compounds that are fully dissociated, and then when they're mixed together, you have an exchange of the cations and anions, and sometimes it results in a precipitation reaction occurring. These exchange reactions are what we're talking about in this type of reaction. So if you think of it that way, as here you had magnesium ion floating around, nitrate ion floating around. It doesn't matter that it came into the solution as magnesium nitrate. Once it hit the water, it dissolves, it's ionized, and now they're floating around. If you think back to some of those early pictures we had, these ions are floating around, and so there's no real requirement that the magnesium stays with the nitrate. It's free to go. In this case, with the hydroxide, the sodium is free to go with the nitrate. And when that happens, we see that the magnesium hydroxide, when those ions get together, and you think about it, magnesium is positively charged, hydroxide's negatively charged. We talked early on that opposites attract. You get that attraction. When that happens, then you get a precipitation occurring, and that will precipitate out of the solution. The sodium and the nitrate, however, if those get attracted to each other, well, nothing's going to happen. They're not going to precipitate or anything like that based on our precipitation, our solubility rules. And so there you'd have sodium and nitrate just still floating around in the solution. So there's just as previously in chapter 3, we're talking about balancing equations. There's ways to balance these types of equations as well, and it's a little bit different than what we did before. So I'd like to kind of go through some of those rules and talk about that and kind of walk you through those different types of balancing and why there are the different ways. So in order to balance one of these reactions, you start out by writing the chemical equation like you normally would. And then you go ahead and balance the equation. The key thing is to make sure your charge is balanced. So if you have a +2 and you as a cation and a -1 as an anion, then you need 2 of those anions to balance out the charge of the +2 charge of the cation. So making sure you have the correct subscripts to balance those charges out. The other thing is going back to that solubility rule table and seeing if something is going to precipitate. When you do this exchange of the cations and anions, do you create a situation where now something's going to form a precipitant? And so if you get that precipitation reaction, then you have to take that into account. And then finally go ahead and balance the whole thing at the end. That's kind of the first step, but the reality is that there's 3 different ways that people will write these reactions. One is the molecular equation, and that's what we've been doing so far, and that's what the class is used to seeing. Then there's something called the complete ionic equation, and that's really a little bit more accurate picture of what it looks like in the solution. And then finally, there's something called the net ionic equation. And that net ionic equation is kind of like what the change is, so to speak, in the solution when you mix the reactants together. So let's talk about these for a little bit so you can see the differences. So the molecular equation should look familiar to what we did in chapter 3. And it's just a normal where you write the different compounds that you're putting together. So in this case, the lead nitrate and the potassium chloride, and then that going to lead chloride and potassium nitrate. We see that it's balanced. So we also see that from our solubility rules, we know that lead chloride precipitates out. So we have a precipitation reaction here. So when we exchange that lead and now it gets exposed to the chlorine, to the chloride rather, we get a precipitant. So this would be how you would normally look at this in the past. But the complete ionic equation gives us a little more accurate picture of what it looks like if we were to analyze what was in the solution. So we see that the lead and the nitrate, that'll dissociate. It's an ionic compound. It's a strong electrolyte. So it'll dissociate into lead +2 ions and nitrate negative ions. And then the potassium iodide will dissociate into potassium ions, positively charged potassium ions, and negatively charged iodide ions. So if we looked at that solution and isolated all the components that were in it, this is a more accurate picture because the lead nitrate doesn't stay as a compound. It does this dissociation. The other thing I want to point out is on this reactant side, look at the 2 in front of the nitrate, the 2 coefficient in front of the potassium, and the 2 in front of the iodide. If we go back to our equation, our original molecular equation, we see where those 2 coefficients came from, number 2 coefficients came from. We have 2 for the lead nitrate. We had 2 nitrate ions for every lead ion. So that's where that 2 came from that subscript down there on the nitrate. For the potassium chloride, we had 2 potassium and 2 chloride molecules in this balanced reaction. So for every mole of lead nitrate, we need 2 moles of potassium chloride. So because of that 2 coefficient in front, when we write this out, we see we have 2 potassium and 2 iodide to make sure that everything is still balanced. When we go over to the products, the lead chloride, the potassium nitrate, notice the 2 in front of the potassium nitrate, that coefficient in front. And because of that, we have 2 potassium ions, excuse me, 2 nitrate ions in our product side. Lead is +2, iodide is -1. So it takes 2 of the iodide to balance out the charge on the lead. So that's why we don't have a 2 in front of the iodine. We have 2 to balance the charge of the lead. And we know from our solubility table earlier, our solubility guidelines, that this is one of the exceptions where I-, when it combines with the cation, forms a precipitant. And so what this is telling us is that we start with all 4 of these ions, the 2 cations and 2 anions on the left. We start with all 4 of those in solution, kind of freely floating around, and then the reaction occurs. And we also see that this reaction just goes one way. It's not an equilibrium reaction. And we know that because the arrow just goes to the right. So in other words, it's gonna go to the right until one of our limiting reagents, whatever that might be, would stop the reaction. If everything's perfectly balanced, it goes all the way. So we form that precipitant, the lead iodide, but then we still have potassium ions floating around and nitrate ions floating around, because those 2, when they associate, nothing happens. We don't get any precipitation. So this complete ionic equation, if you compare this information to the information in our molecular equation, we see that the molecular equation is great. It tells us what was the reactants and what are the products, gives us some information, but this complete ionic equation form really is telling us a little more information about what the state of the different ions are. So one thing you'll notice though is we've got some things on the right-hand side of the equation, and they're the same thing as on the left-hand side of the equation. when we look into that, that leads us to what is called the net ionic equation. And this is where you get rid of, when you write this equation, you get rid of things that are the same on the two sides of the reaction equation. And so if we go back here, we see that there are 2 nitrate ions and 2 potassium ions on the left, and 2 of each of those on the right. So we could cancel those out. We can't cancel the lead because it's +2 on the left, but it's part of the PbI2 molecule on the right. Same for the iodide ion. So these ones that are the same on each side are called spectator ions. And by that, it just means they're not participating in any kind of reaction. In this case, it's a precipitation reaction, but they're not participating in anything like that. So if you cross those out, you just get the remaining ions, and that's what this equation down at the bottom is. That's the net ionic equation. And so what that's doing is that's telling us really what the actual action is in the reaction. And it's lead +2 reacting with iodide to form lead iodide and having that precipitation occur. So let's just go back for a second and look at these 3. We said for these exchange type reactions, there's 3 ways that people tend to write these, and each one give them a little bit different information. You have that molecular equation, the complete ionic equation, and then the net ionic equation. That molecular equation, it's nice. It's what we're used to seeing because it tells us what are the reactants, what are the products. It tells us if things are in aqueous solution or if they're solid or whatever. So it gives us a fair amount of information. If we want to know exactly what's going on in terms of the state of all the ions, this complete ionic equation does a little better job of that because it's telling us right off the bat, okay, the lead and the nitrate, that's dissociated. Those ions are floating around. Same with the K plus and I minus ions. It's telling us all that. So we know what's floating around. For me personally, it makes it a little easier to see what that exchange would be. I can see, oh, Pb +2 would go with I minus, and I would need 2 of the I's minuses to balance the charge out. The NO3 minus, that would go with K plus, or rather, that would go with K plus, and so I can see there what that exchange looks like. And then once I see what the new compounds are after the exchange, I can think back to my solubility tables, my solubility guidelines, and say, okay, usually I minus is soluble, but I remember lead was one of those exceptions. So I'm going to get a solid form with that. Nitrate, NO3, that's always in solution. So I'm good with that. And potassium, those are usually in solution too. So those potassium ions and those nitrate ions, even though they may associate together briefly, they're not going to do anything and form any reaction. So writing it this way just makes it a little easier in my mind to kind of see what those new combinations would be. And then finally, net ionic is if you're really trying to get down to the meat of the problem, so to speak, it's, well, lead reacting with iodide and something precipitates out. And that's kind of like the condensed version of what's going on. So depending upon what you're trying to express and how you're trying to express it, you'd use one of these 3. But that's kind of the reasoning behind the different ones and the logic behind it. I'll say it again just because we used it here and I said it earlier, but we see that one of the keys to writing these reactions is knowing those solubility guidelines so we know if something's going to precipitate out or not. If we don't know that, we can't write these equations. So there is some homework associated with this to give you some help with writing these kind of equations and stuff. The one thing I will point out on 4.29, B the answer for B should be true, not false. Any questions on what I covered before I move to the next part? Okay, I'll keep moving along then. Okay, let's talk a little bit about acids and bases. So acids are substances that ionize an aqueous solution to form hydrogen ions or protons. So hydrogen ions, protons, those terms are used interchangeably. Acids are often called proton donors because they give up this hydrogen ion. And here's some examples of some common acids. So hydrochloric acid, nitric acid, sulfuric, acetic acid. When you see these inorganic compounds like the HCl, HNO3, H2SO4, and you see that hydrogen at the very beginning of the molecular formula, that's usually a good indicator that it's an acid. So that hydrogen on the HCl will get donated, on the nitric, the sulfuric, both of those will donate. The first one comes off a lot easier than the second one. Now acetic acid, that would be considered an organic acid because it has carbon in it. And those acids, the hydrogen all the way to the right, the one next to the oxygen, that's the acidic proton. That's the one that'll get donated. The three hydrogens that are between the two carbon atoms, those three hydrogen atoms are bonded to that first carbon. Those typically don't get donated. So in these types of compounds, it's often that last hydrogen, and looking at the formula, that is the acidic proton. Okay, bases are kind of the opposite of acids. Acids want to donate a proton. Bases want to give off hydroxide and accept protons. And so when bases are dissolved in water, you get OH produced. When acids are dissolved in water, you get hydrogen ions or protons produced. Bases, however, don't have to contain OH to be a base. And the biggest example of that is ammonia. So NH3 goes to NH4 ammonium, and that is it's considered a weak base, but it doesn't have OH in there anywhere. So there are bases, there are quite a few bases actually that don't have OH on them, but we'll talk about that a little more later. So when you have acids and bases, you classify them kind of like we did the electrolytes, strong and weak. And so strong acids and strong bases versus weak acids and weak bases. The strong acids and bases, basically when you put them in water, they dissociate completely. And here are some examples of that. So you have hydrochloric acid, hydrobromic, chloric, perchloric, nitric, sulfuric. That first proton on sulfuric is the strong acid part. So it means you put that into solution, it dissociates, you donate all the protons, there's not that equilibrium coming back. Same with the bases. Sodium hydroxide, potassium hydroxide are probably the most common ones, and there's some others listed there as well. You put sodium hydroxide, potassium hydroxide into water, it dissociates fully. So all that hydroxide becomes available. So strong or weak electrolyte. Let's talk about that a little bit with regards to this. If it's ionic or molecular. So if it's ionic, then it's always going to be a strong electrolyte because that implies that it dissociates fully. If it's ionic, and we're assuming these are soluble. I know we talked about some ionic compounds aren't soluble, but for this discussion, let's assume everything's soluble. So if it's ionic and soluble, it's a strong electrolyte because by definition, everything dissociates. If it's molecular, then if it's one of those strong acids or bases, like we just saw on the table, then that'll be a strong electrolyte, because if it's a strong acid or base, we're saying it dissociates totally into the cation and anion. If it's a weak electrolyte, so in other words, if it's a weak acid or base, then it doesn't dissociate the whole way. We have that equilibrium. So in other words, like with the acetic acid, we have the double arrow. And then because it doesn't, those types of acids and bases, acetic acid, ammonia, things like that, since those don't dissociate totally, those are considered weak electrolytes, weak acid bases, weak electrolytes. And then finally, if it's a molecular compound, but doesn't dissociate at all, then it's a non-electrolyte. The example we had earlier on was the sugar. So once again, the electrolyte, even for the acids and bases, just as with the ionic compounds, comes back to how much it dissociates. So when we're dealing with acids and bases, we have something called neutralization reactions. So if you have an acid and a base, so you have something with a bunch of protons, something with a bunch of hydroxide ions, you combine them, they react together to form water, and you get a neutralization reaction. And so, so let's talk about these a little bit. So here's an example of hydrochloric acid, HCl, and added to sodium hydroxide, NaOH. And if we look at those three types of equations that we talked about a little while ago, the molecular equation, the complete ionic, and the net ionic, let's go through those to get a better picture of what's going on in these neutralization reactions. So we have our first molecular reaction written out, but then let's go to the next reaction, the complete ionic. And we see that for HCl, that's a strong acid. It's a strong acid, so we know it's going to dissociate fully. It's going to be a strong electrolyte. So we have hydrogen ions plus chloride ions. We look at that sodium hydroxide, and the sodium hydroxide is a strong base. We put that into aqueous environment, and we're going to get complete dissociation of that. So we have sodium ions, and we have hydroxide ions. So then we do our exchange, right? Now we match up the hydroxide ion with the proton, and we match up the sodium ion with the chloride ion. Well, H plus OH minus, that's water. So that's going to combine to form water. Sodium and chloride, we know from our solubility rules that sodium and chloride are soluble. There's no precipitation or anything like that forming. So then we have sodium ions floating around and chloride ions floating around. We formed some additional water. And now we look at our net ionic reaction, canceling out those spectator ions. In this case, it's the chloride and the sodium ions on each side we cross out. We get that a proton plus hydroxide gives us water. And so when we talk neutralization, that's really what we're talking about. Neutralization means you're getting rid of the protons, you're getting rid of the hydroxide, you're neutralizing them, you're erasing them, however you want to think of that. And that's what goes on in these neutralization reactions. So typically what happens is you get this, when the base is a metal hydroxide, you get water and a salt that are produced. And in this case, the salt is the sodium and chloride, and then of course the water molecule. There are some neutralization reactions where you can get a gas formed as well. So once again, we do this exchange reaction. And in this case, we're looking at a reaction that involves carbonate and another one that involves bicarbonate. And with those carbonate type compounds, it's real common to get carbon dioxide as one of the products. And we see in this case that we have calcium chloride formed, aqueous. So because it's written aqueous like that, we know it's in solution. And then we have CO2, carbon dioxide. And because of the little g in the parentheses, that tells us that that's a gas. And then water, liquid as well at the end. So the CO2, if the one lab that we were doing and we were going to do some mixes, but we didn't have enough time to do it, we would have seen this reaction in there. One of those was a carbonate, acid carbonate reaction, and you would see a bunch of bubbles is what you would do. So in these kind of reactions, you get that. These carbonate type reactions to neutralize acids, because this is a neutralization reaction, and we know that because on the left-hand side, we have protons. On the right-hand side of the reaction, there's no protons left, right? They're all gone. And so that tells us we've taken something that was acidic, and by acidic it means we have a bunch of protons, free protons present, and we've neutralized them. We've gotten rid of them so there's not free protons floating around. Where using these carbonate, bicarbonate type compounds to neutralize acid is really common I'm going to skip forward to here. That's what you get in these neutralization reactions for things like Tums and Rolaids and things like that. That's the chemistry behind those kind of products. There's some others listed here as well. But a lot of them, the Rolaids and Tums, are carbonate type, Alka-Seltzer, carbonate type reactions to neutralize the acid in your stomach. The other kind of reaction that gives off a gas that a lot of people are familiar with is one that forms hydrogen sulfide. So that's the H2S on the right-hand side of the equation. So in this case, it's sodium sulfide plus sulfuric acid gives you sodium sulfate and H2S. Hydrogen sulfide is the gas that kind of smells like rotten eggs. So people will smell that. Hydrogen sulfide sometimes is what they'll put in the gas that you have in your house, a real small amount, so that if something goes wrong, you smell it, because the gas that used to heat your house doesn't have any smell. So if you do smell something, it's an additive, and sometimes they'll put real low levels of this in it. But that rotten egg gas smell, I'm sure you've smelled it at some point in your life. It's pretty stinky. So let's talk a little bit about oxidation and reduction. So oxidation, the definition of oxidation is loss of electrons. The definition of reduction is gain of electrons. So if an ion or a compound or something loses electrons, oxidation has occurred. If it's picked up electrons, then reduction has occurred. The way I always think of that is like with reduction, gain electrons, is if something starts out at +2 and then goes to a charge of 0, then it would have had to have picked up 2 electrons in order for that charge to go down by 2. And I think of it as, oh, I went from +2 to 0. That's a reducing of that number, of that charge. And that's how I remember that gaining electrons is reduction. If you have a better way to remember it, great, but that's kind of how I do it. The important thing to always remember about oxidation reduction reactions is that you can't have one without the other. So in other words, if something's oxidized, something else had to be reduced, because you have to have that movement of the electrons. And so if you never have just oxidation or just reduction, you always have them in tandem with each other. And these types of reactions, these oxidation reactions, are called redox reactions. So you'll hear people talk about redox reactions all the time. This is what they're talking about. Okay, a couple other things to help you understand oxidation and reduction. So you always have it with the electron movement, but there are couple other tips that you can have to know if something is oxidation occurring or reduction. If you gain oxygen, so in other words, if a molecule picks up oxygen, then that's an oxidation process. If you lose hydrogen, that's an oxidation process. In addition to losing the electrons. So any of those three could indicate oxidation has occurred. We said that oxidation and reduction must match up. You can't have one without the other. So if you've got something that's undergoing one of these three things for oxidation to occur, then something else had to have the opposite happen to it for reduction part. So that could be, reduction could be loss of oxygen, gain of those electrons, or gain of hydrogen. So any of those three can indicate oxidation or reduction. Something that can be a little confusing is when people talk about oxidizing agents themselves are actually being reduced. So oxidizing agents tend to gain electrons easily. So in other words, they get reduced to help other things become oxidized. And just the opposite with reducing agents. They tend to lose electrons readily so that they are oxidized during that. So sometimes you hear people say it's an oxidizing agent. If it's an oxidizing agent, it's not being oxidized, it's being reduced. If it's a reducing agent, it's being oxidized. So this definition, oxidation, reduction, is slightly different than an oxidizing agent and a reducing agent. So I would suggest you take a little bit of time and look those over so you get comfortable with kind of the subtle distinction between these different terms. Okay, one of the things that you'll do to try and understand if things are being oxidized or reduced, especially when you're trying to figure out if stuff's picking up electrons or losing electrons, is we'll talk about oxidation numbers. Oxidation numbers are just kind of a tracking thing. They're not meant to be that these atoms actually have these charges. It's just a way to express things so you can figure out if something's being oxidized or reduced. So we're going to talk a little bit about, in general, how you try and figure out oxidation numbers, so then you can figure out if stuff is oxidized or reduced. Okay, so some rules associated with assigning oxidation numbers. And so these oxidation numbers are assigned to the atoms that are within the molecule. And we'll see some examples of this. So atoms in their elemental form have an oxidation number of 0. The oxidation number of a monatomic ion is the same as its charge. Non-metals usually have negative oxidation numbers, although they can be positive under certain circumstances, but usually they're negative. And remember, the non-metals are the things in the upper right-hand corner of that periodic table to the right of the stair-step thing. So that would be carbon, nitrogen, oxygen, stuff like that. Oxygen is usually -2 unless it's peroxide. If it's peroxide, remember peroxide is like H2O2, that type of thing, then it's a -1. But usually oxygen is -2. Hydrogen is +1 usually when it's bonded to a non-metal. So in other words, when it's in like an organic compound type situation, it'll be +1. It can be -1 though if it is associated or bonded to a metal, but usually hydrogen is +1. Fluorine and the other halogens are usually -1. There's some exceptions when it's with oxygen, but usually those halogens, fluorine, chlorine, bromine, those kind of compounds are -1. Okay, the sum of the oxidation numbers in a neutral compound is 0. So in other words, when you look at the different atoms in a compound that overall has no charge, then those oxidation numbers have to add up to 0 to match what the compound is. The other thing to remember is when you have a compound, if you have like C12, H22, O16, or just whatever the subscripts are, you have to take into account the number of in the subscript. So if it's H16, for instance, it'd be 16 times the +1. So it'd be plus 16 in that. So when you're trying to balance out the charge in that molecule, you got to take into account how many of those atoms are in that molecule. So that subscript is real important when trying to figure out the oxidation numbers. So here's a couple of examples. So the first one, O2, that oxidation number for oxygen would be 0 because we said when it's in its elemental form, it's by definition 0. For water, H2O, water's usually +1, oxygen's usually -2. If we see if this balances, we have hydrogen with +1. There's 2 of those, so that would be a +2 charge associated with the hydrogens. And then we have 1 oxygen. That's typically -2. -2 +2 balances out to 0, so we're good there. Let's look at sulfuric acid. So we have 2 hydrogens. Hydrogen's usually +1, so that's a +2 there. We have 4 oxygens. Usually oxygen is -2. So 2 times 4 is 8, so we have -8 from the oxygens, +2 from the hydrogens. That tells us that sulfur, to balance this out, has to be an oxidation state of +6. So probably didn't know what sulfur is. I know I didn't off the top of my head. I certainly wouldn't have said +6, but I do know oxygen's usually -2, hydrogen is usually +1. So, and I know that it's got to balance out because H2SO4 doesn't have a charge. So I could use that information that I had from my general rules to calculate what the charge contribution is for oxygen and what it is from hydrogen. And that allowed me to figure out my oxidation state of sulfur. H2O2, that's peroxide, so that's that exception for the oxygen. So we see oxygen is -1 there. And then the last one, potassium acetate. Carbon's usually 0 in these organic compounds. It's usually 0. As you can see here, it says depends. It's not always 0, but usually it's 0. So for me, what I would focus on in this one is, I know hydrogen is very likely to be +1. I've got 3 hydrogens, so I got +3 there. I know oxygen is usually -2, and I've got 2 of those, so that's -4 there. Potassium, that's one of those 1A elements. Those are usually +1. So if I balance that out, +3 from the summing up the 3 +1 hydrogens, +1 from the potassium, that's +4 total. I had 2 oxygens, each -2, so that gets me to -4 there. So I'm balanced right there. That further supports that those carbons are 0. So just kind of like with the H2SO4, where I had hydrogen and oxygen, which I had a certain level of confidence. I knew what those were, and I could figure out sulfur from that. It's kind of the same with this potassium acetate. I'm confident that I know hydrogen, oxygen, and potassium. And if I calculate those out, I see that, yes, that supports that carbon is 0. So, like I said before, this is just a tool to figure out the oxidation states. So then, for instance, with the sulfur, with H2SO4, if I did some reaction where the oxidation state of the sulfur changed from +6 to +4, would that have been reduced or oxidized?
Was it a sulfur change?
Yeah.
Reduction.
Yep, it'd be reduced because I'd go from a +6 charge to a +4 charge. Very good, thank you. Sorry putting you on the spot there.
I was just trying to make sure.
And so that's where you would use these kind of oxidation number calculations to get a feel for if something's being oxidized or reduced. Okay, there's another type of reaction called displacement reaction. And this is where ions oxidize an element. So in other words, in this example, The proton oxidizes magnesium. And so by proton, we're talking about really an acid reacting with a metal. So we see HCl down at the bottom reacting with solid magnesium, and we see the oxidation numbers are +1 for the hydrogen and -1 for the chloride. We go and do the reaction and we get hydrogen gas formed. By definition, the hydrogen will have an oxidation state of 0. And we see the magnesium goes from an oxidation state of 0 to an oxidation state of +2. So we know that the magnesium has been oxidized because its oxidation number went from 0 to +2. So to do that, it had to lose electrons. This table 4.5 is what they call an activity series. And what this tells us is how reactive metals are in aqueous solutions when you add acid to it. And so if you look about 3/4 of the way down the table, you see hydrogen reaction in blue. All the elements above hydrogen, so lead, tin, nickel, cobalt, on down the line up until lithium, all the ones in this table that are above it will react with acid to produce hydrogen gas. So in other words, you get a reaction, like here we got a reaction and produced hydrogen gas in this example here, HCl and magnesium. Here, this table is telling us all of the metals that are above the hydrogen line will react. The ones below, copper, silver, mercury, platinum, gold, those don't react in acid. So, and you see gold's at the bottom, and what that tells us is gold is the least reactive. That's one of the reasons gold is valuable, is that it doesn't react with stuff very well. So it's real, from an industrial perspective, it's real sturdy. And same with platinum. But that's part of the reason gold and platinum have a lot of value, is that limited reactivity. It's hard to mess them up, basically. So as I said on that table, this table here, the higher it is up on the table, the more reactive it is. So lithium is a very, very reactive metal, for instance. Potassium also, sodium as well. Okay, so there's some homework associated with this section that we just covered. Please take a look at some of that. The next thing we're going to do is we're going to talk about solutions and molarity in that. We're going to do that on Wednesday before the quiz. So we're going to wrap things up here for today. Just want to repeat again that on Wednesday, we'll finish off this chapter. Then we'll have a quiz. The quiz will be on chapter 3 only. If you want to come into class to take the quiz, you're welcome, or you can take it remotely. That's up to you. I will be at class because I'll be lecturing at the beginning of the class. So any questions about anything before we sign off? Okay, thank you.
Thank you.